So we're going to kick off the next section with something which is a little still. I mean, when Randall and I worked on lining up speakers, we kept the idea of citizen science, but also our friends from the AAVSO, variable stars, and that kind of thing. So we try to recognize that. And so our next speaker is Dr. Gregg Wade, who's the head of the Department of Physics and Space Science at the Royal Military College at Queen's. And his talk is about BRITE, which is a constellation of tiny satellites. And many of you may know or have heard of the MOST satellite, which was something that was a project from out in Vancouver, UBC. The Americans put together, they got the money to build the Hubble. Canadians have to do more with less. And so MOST was, and I think our speaker will talk a little bit about MOST, it was about the size of a suitcase. And it was called the Hubble Space Telescope. And the thing was, it performed brilliantly. I heard recently that I think they finally lost communication with it. So it's, spend a moment's silence for MOST, but it behaved beyond its expectations. So please join me in welcoming Gregg Wade and his talk, BRITE Constellation, Tiny Satellites for Big Science.
Morning, folks. How are we doing today? Good. So we're post-coffee break now, so everybody from the West Coast should be more or less awake. Very glad to see you. As Randy said, I'm going to talk a little bit about the BRITE Constellation mission today. It's a privilege to be here to be able to speak to you, and I'd like to thank the organizing committee for the opportunity to represent the BRITE team at your General Assembly. BRITE stands for Bright Target Explorer, and the BRITE Constellation mission is a space astronomy mission that is meant to focus on the brightest stars in the sky using unconventional technology. And in particular, the mission relies on nano satellite platforms in order to observe stars that you can see with your naked eye. Canada is one of 3 partners in the mission. The 3 partners are all small countries with limited space program budgets. And so this is a project that is well focused on the scale of the space budgets in those 3 countries. So the countries themselves are Canada, Austria, and Poland. So an interesting triumvirate of countries, particularly when you notice that the flags all have the same color scheme. That wasn't a prerequisite, but it's still the case. The mission itself would not have been possible without contributions from 2 key organizations. The first is the University of Toronto Institute for Aerospace Studies Space Flight Laboratory, the SFL, who were responsible for the construction of the satellites and who perform a component of the operations of the mission. The second contribution was from the Canadian Space Agency. The CSA was responsible for funding the construction of the satellites, and they continue to fund the operations of the Canadian satellite called BRITE Toronto. All right, so BRITE Target Explorer, the BRITE Constellation, is a space astronomy mission that is meant to obtain precision photometric measurements, so brightness measurements, of the brightest stars in the sky. And it needs to focus on the brightest stars because, as we're going to see, its telescopes are smaller than Galileo's telescope. They have an aperture of only 3 centimeters in diameter. And the goal is really to understand the physics of these bright stars in a way that can't be achieved from the ground. So the particular focus of the mission is to understand rotation, is to understand pulsation, mass loss, and in general, the recycling of material that leads to the ecology of the galaxy. So when we talk about ecology on Earth, we talk about the cycling of material, the cycling of energy and other quantities, and the way that these cycles support themselves. And the same is true in the case of the galaxy. The interstellar medium is responsible for the formation of stars. Those stars ultimately complete their evolution and release their material back into the interstellar medium to form the next generation of stars and, of course, planets, and ultimately of life like we see here on Earth. And so this is the idea behind astrophysical recycling. Material that ultimately begins its life in the interstellar medium, forms stars, and through BRITE we can analyze the ways in which that material is returned to the interstellar medium. So this is a space astronomy mission. We're focused on precision photometry, but as we heard, the Canadian space budget is low, and so we need to develop space missions that are either highly collaborative or that are intrinsically inexpensive, and BRITE is both. We're going to hear about a larger space mission this afternoon, the JWST, in which Canada has an important role, but of course Canada isn't the driver. In the case of BRITE, Canada was the originating location of the idea and was responsible for the initial proposals that went to describe the mission. I'm going to tell you a little bit about BRITE in the context of these larger space missions. So you're all familiar with this guy. This is the Hubble Space Telescope, an optical UV telescope that's been in space now for roughly 30 years. The budget for the Hubble Space Telescope was about $2.5 billion US. And that includes a couple of space missions that went up initially in order to replace the optics, which were poorly figured, as well as to replace instrumentation. And so this is, by all measures, been a very highly successful space mission. But again, the cost is measured in billions of dollars. And I mentioned the James Webb Space Telescope that Natalie is going to be telling us about later. So the JWST, Natalie will confirm for us that it's going to be launched in 2021 at this point. When it's launched, at that point, it's expected that the cost of the James Webb Space Telescope will be roughly $10 billion US. So these are extremely expensive missions. They have diverse and ambitious scientific goals. They have relatively long lifetimes, but ultimately they're out of the price range for Canadian astronomers. And so it's worthwhile at this point to think a little bit about why we bother putting telescopes in space, why we spend billions of dollars to launch telescopes into orbit around the Earth or even far away from the Earth, when we can spend 1,000 times less in order to construct even larger telescopes on the Earth's surface. And the answer to that, I'm having some interesting slide effects here, but that's okay, we can ignore that. The principal reason for sending telescopes into space is because the Earth has an atmosphere. Right? The answer is it's the atmosphere dummy. Because the atmosphere ultimately blurs images, the principal reason for launching the Hubble into space. The atmosphere absorbs at certain wavelengths, so the principal reason for launching JWST far from the Earth is because the Earth's atmosphere is not transparent at the infrared wavelengths that it is attempting to observe at. The weather, of course, controls our ability to observe things from the Earth's surface. And ultimately, because we're stuck on a planet that rotates every 24 hours, we have to contend with the day-night cycle. We can't observe 24 hours per day. And so these are real tangible benefits to launching telescopes into space, but at the same time, they're expensive advantages. And so the idea behind BRITE, and as we're going to hear, MOST, was to improve the cost-benefit ratio to achieve these same benefits while spending far less. So this is the MOST Space Telescope shown to scale with the Hubble Space Telescope. MOST stands for Microvariability and Oscillations of Stars. MOST was Canada's first space telescope. As Randy told us, it was given the moniker the Hubble Space Telescope, roughly the size of a large suitcase. It was launched in 2003 and has only recently come to the end of its mission. So extremely effective space telescope, all for the cost of only 10 million Canadian dollars. So we're talking about a factor of 1,000 cheaper, in the case of JWST, 10,000 times cheaper than the cost of these large space missions. And so the idea behind BRITE is to build on the heritage of the technologies and the procedures that were developed for MOST in order to take advantage of the miniaturization of space technology in order to continue to observe bright stars in the sky. And so this is a BRITE telescope to scale. It's not a real picture, of course. So the BRITE telescopes are built on a 20 centimeter cube nanosatellite platform, and they cost about $1 million a piece. And so for that price, if you can build one, why not build 6? And so that's what we've done. By collaborating with Poland and with Austria, each of the countries has been responsible for the construction of 2 of the BRITE constellations of satellites. So I'm going to tell you a little bit more about what we see inside each one of these satellites, and ultimately how the mission works, and then I'll finish off with a discussion of some of the recent science results. So in terms of their physical size, the best comparison that we found for a BRITE satellite is roughly a car battery. So a BRITE satellite is just a little bit bigger than a car battery. It's an object that you could physically pick up. You could carry it around with you. In fact, one of our Austrian colleagues has recently constructed a Lego model to scale of one of the BRITE satellites. I'd hoped to be able to construct my own before I arrived here today, but the parts are still in the mail. So if you have a look at a BRITE satellite in reality, so on the right-hand side, this is one of the BRITE satellites before it was launched into space at the SFL. So you can see that it's a beautiful golden color. It's got a magnetometer and magnetorquer that's sticking out the top. And most of the surface is covered either in antennae or in solar panels in order to provide the power that's necessary for the mission. Of course, the satellites themselves wouldn't be of much interest without an astronomical instrument. And so the principal payload of each of the telescopes, of each of the satellites, is a small telescope with a 3-centimeter diameter primary lens. So these are refracting telescopes that are meant to produce images of large fields of stars that are focused on the CCD. If we look inside the box, there's a tremendous amount of technology that's been miniaturized in a very effective way in order to allow us to carry out this very specific mission with these tiny satellites. So you'll notice that the interior is structured into 3 trays. Those trays are focused either on the payload itself. So in the bottom tray is located the telescope as well as the star tracker. In the middle tray are the electronics associated with the control of the satellite. And then in the upper tray are 3 small reaction wheels that I'm particularly interested to tell you about. The satellites themselves are relatively light. I said you could pick them up and carry them around. They're about 7 kilograms each. They only use about 7 watts of power, so you can think about the power that's consumed by a very efficient fluorescent light bulb is several times as large as that. And the key to achieving the scientific objectives of the mission is to stabilize these tiny boxes while they orbit around the Earth. And that's achieved using a system of attitude determination and control electronics and instruments. But the most interesting element of the attitude control system are 3 tiny reaction wheels. So that's what are being shown here. They're each big enough that I could hold them in my fingers. And the way in which they've been oriented here shows you how they're oriented within the spacecraft. So these are tiny little metal wheels. They're actually made of aluminum. And they're caused to spin in one direction or the other. And in order to maintain the angular momentum of the spacecraft itself will counter-rotate according to the direction of the wheels. And so we use these tiny reaction wheels in combination with star and sun trackers, as well as magnetometers and magnetorquers, in order to point the telescopes toward particular regions of the sky, and then to maintain that pointing stably while they obtain their observations. So these are really beautiful little pieces of technology. So the satellites themselves are in low Earth orbits. The orbits are polar, so they pass over the North and South Pole. The periods are about 1.5 hours, so they're a little bit higher than the International Space Station. I mentioned that there were 6 satellites in the constellation. The satellites themselves were launched over a period of time between 2013 and 2014. The first 2 to go up were the Austrian BRITE satellites. They were successfully launched from an Indian launcher, and they were successfully placed into orbit and began their observations that year. The remaining 4 satellites were launched over a period of time in 2014. The 2 Canadian satellites, BRITE Toronto and BRITE Montreal, were launched on the same rocket. BRITE Toronto was one of the first of 32 nanosatellites that was ejected from the rocket. Unfortunately, BRITE Montreal was meant to be the last that was ejected from the rocket. And it seems that the power system that provided that little boost of energy, the burning of a piece of fabric that maintained the connection between the rocket booster and the satellite itself, had run out at that point. And so it seems that BRITE Montreal is still orbiting around the Earth inside the Russian rocket booster. So ultimately, our constellation of 6 satellites has turned out to be a constellation of 5 satellites. Nevertheless, because we planned on having redundancy within the system, we're able to carry out all of the scientific functions of the mission. So we communicate with the satellites using a system of ground stations, one that's located in Graz in Austria, one that's located in Warsaw in Poland, and the third one is located here, just north of Toronto, in fact, slightly to the east of here at the SFL campus. So this particular image shows an example of the Graz ground station. You can see the principal antenna that's used for uplink and downlink of data. There are some screenshots that allow us to know where the satellite is located. And you can see the interior of the control room. So we have dedicated controllers who are responsible for maintaining communication and downloading data from the satellites 24 hours a day. So I mentioned that the telescopes of the BRITE satellites were designed in order to observe large regions of the sky. So I don't know how well you can see this here. I can't see it particularly well myself. So this is a picture of the constellation of Orion. It's located inside the circle here. And what I'm going to do is overlay a full frame image obtained by one of the BRITE satellites. If you can see that, you'll notice that that full frame image includes the entire constellation of Orion. You can see the belt, you can see the sword, you can see the shoulders, you can see the knees. Now, because our satellites are tiny, our antennae are tiny too, and that means that our ability to downlink data and uplink commands is very limited. So that means that we want to deal with the smallest amount of data possible. And so rather than downlink big images like this, what we do is to identify the stars of interest, typically the brightest stars, within a given field, and to isolate those stars in tiny little postage stamps. You can see that a little bit. So what's being shown here is, again, this is Orion. It's tilted on its side, and there's a tiny little box around each of the brightest stars in the constellation. And then BRITE points at those stars and obtains tiny little images of each one of them that are ultimately downlinked. So what I'm showing here are examples of these postage stamps for stars in the constellation of Orion. On the left-hand side, from one of the BRITE satellites that has a blue filter, and on the right-hand side, one of the satellites that has a red filter. So in each one of those, you see that there's at least one star, but you'd certainly not want to publish these in an astronomy magazine, right? These are really terrible images. And that's because the goal of BRITE Constellation isn't to obtain pretty pictures, but rather to obtain precision measurements of stellar brightness. And by blurring the image, by defocusing the image over multiple pixels, we're able to reduce the effect of systematic errors, flat fielding, if you will, that impact smaller images that are focused on a smaller number of pixels. And so the idea is that each BRITE points at a particular constellation for a long period of time, up to 6 months at a time, and obtains measurements of the brightness of each one of these stars. So a typical data set might look like this. So on the x-axis is magnitude, so brightness. On the y-axis is time. And it's a little bit small for you to see, so I'll read it off. So the total time scale here is about 20 minutes. That's the period of time during which a typical BRITE satellite will observe a star during each orbit. After 20 minutes, enough data has been collected that we're not likely to exceed our downlink capacity, and so the satellite stops observing at that point. So every orbit, the satellite returns to observing the field, and so we obtain these clusters of observations that are spaced roughly one orbital period apart, so about 98 minutes apart. And then those observations are acquired over a period of months and ultimately come together into a beautiful data set like this. So what you're seeing here in black are the raw observations, and then in red they've been averaged over each one of the orbits. And if I zoom in on a tiny piece of that light curve, what you'll see is the light variation due, in this case, to a slowly pulsating B-type star. So this particular star was studied by Thomas Kallinger and was discussed in more detail by Andrei Popovich. And this is an example of the kind of data set, the kind of quality of data that the BRITE satellites are able to acquire. Now, if you look really carefully, you may notice that in behind the black dots in this picture are red dots as well as blue dots. And so those correspond to observations that are normally obtained simultaneously by the BRITE satellites that have red filters and the BRITE satellites that have blue filters. And then we do this for about 6 months at a time. So how many of you here are familiar with the TESS mission? And so most of you will probably know that the typical TESS data set is 28 days long. Right? So although TESS and BRITE have very similar scientific priorities, they observe many of the same stars in the sky, BRITE's typical data set is many, many times longer than TESS. Moreover, BRITE is able to return to the same fields year after year to acquire secular observations of these same systems. And so there's huge legacy value in the data set. So this is a projection of the bright stars in the sky. So what we're looking at here is the entire sky, both hemispheres. And each one of the stars in the sky brighter than about 6 magnitude is encoded with a symbol that has a color that tells you about its spectral type and a shape that tells you about its luminosity class. And then the circles illustrate the different fields that have been observed by BRITE up until this point. So we've observed 42 different fields, starting in early 2014 once we got the kinks out of the mission, and we continue to observe to this day. So this is a slightly different representation of the same thing. So the names of the fields are shown on the vertical axis, and then time is on the horizontal axis. Each one of these bars represents a period of time during which the field was observed, and you'll notice that typically they come in pairs, right? So typically one of the blue satellites and one of the red satellites are observing the field at the same time. In the case of Orion, so at this particular point, we'd observed Orion 5 times, 1, 2, 3, 4, 5, and in fact, we've just returned to Orion for the coming season. And so Orion is an example of a legacy data set that provides us not only with precision photometry on timescales of half a year, but also revisits of that field every year for, at this point, about 6 years. Okay. So what I'd like to do at this point is to tell you a little bit about the science of BRITE Constellation. So I'll provide you with a little qualitative introduction of the science we're trying to do, and then I have 4 or 5 different examples of recent science results that I'll tell you about. So I mentioned that the principal priorities of BRITE Constellation are to study stellar rotation, stellar pulsation, and the ecology of the galaxy, so mass loss in particular. So everyone is familiar with a picture like this. This is a picture of the sun taken in white light, and of course you can see a very large active region with sunspots. Those sunspots, of course, come and go, and as they do so, the surface of the sun becomes marginally brighter or fainter if there are more sunspots. And of course, as the sun turns with its roughly 1-month rotational period, those spots can also come in and out of view. In fact, this is how Galileo determined initially the rotation period of the sun. And so we can imagine using BRITE Constellation to observe distant stars for which we can't resolve the surface in order to infer the presence of spots and understand, for example, their activity cycles. A second focus of BRITE Constellation is to study companions of stars. So if I were talking about the Kepler mission or the TESS mission, I'd probably be focusing on exoplanets in this particular case. So transiting exoplanets that cause minute decreases in the brightnesses of stars. Because BRITE Constellation is a tiny telescope, typically we're not sensitive enough to be able to detect exoplanets. So instead, we study stellar companions. And so by examining eclipses or even distortions of stars as they orbit around one another, we're able to infer the physical properties of those stars and better understand the physics of stars in general. So I mentioned astrophysical recycling. So the mass loss from stars, you're probably all familiar with the solar wind. More massive stars in the galaxy lose much more material over the courses of their lives, as well as redistributing all of their material, essentially, over the galaxy at the ends of their lives in the form of supernovae. And then thinking back to the image of the slowly pulsating B star I showed you, a final focus of BRITE science is to examine pulsations or oscillations in stars. So using techniques that are similar to those of terrestrial seismologists, we can use the oscillations of stars in order to probe the density and temperature structure of their interiors. So with those as introductions, I'll tell you a little bit about five science results that particularly excite me. So the first one here is an example of the detection of bright spots on the surfaces of hot supergiant stars by a PhD student at the University of Montreal. So what's illustrated on the right-hand side is obviously an artist's depiction of the surface of a hot star with streams of wind that are leaving its surface. And we know those streams of wind are there thanks to space missions that observe in the ultraviolet, like the Hubble Space Telescope. But what hasn't been known up until this point is why they occur. And so what this PhD student discovered is that this particular star, Zeta Puppis, varies in brightness with a well-defined period of about 1.5 days. And he inferred that periodic variation was due to the rotation of the star, similar to the sunspots I was telling you earlier. But he observed that the light curve of the star changed its structure with time. And so what he inferred, I'll see if I can illustrate this with my, can you guys see that? There we go. So what he inferred is that the change in the light curve corresponded to the presence of bright spots on the surface of the star. And as the star rotated around, we were observing the modulation of the brightness, and that those bright spots were changing their structure and distribution as a function of time. And so this was the first detection of bright spots on the surface of a hot star. It stands in clear contrast with the dark spots that we see at the surface of the sun. These are currently unexplained, so a very interesting discovery. BRITE is focused on the class of BE stars, so these are rapidly rotating hot stars. They spin sufficiently quickly that material at their equators is very loosely bound to the star. And so it's almost able to be launched into orbit. And the key scientific question over the last 20 years has been, what is the mechanism that provides that little bit of extra energy that launches the material into orbit around the star? And we know that the material is being launched into orbit because BE stars, the E stands for emission. Right? So BE stars have disks of material that have been launched from the surface that surround them. And so one of the discoveries that we've made with BRITE Constellation is that when BE stars, like the one illustrated here, eject material, they brighten. And if you look carefully at the light curve, particularly in this region here, you'll notice that there are periodic oscillations. And so the discovery with BRITE is that those periodic oscillations seem to be the mechanism that provides the energy to launch that material off of the surface. We've been very interested in studying eclipsing binary stars, as well as a class called the heartbeat variables. So these are stars that don't quite eclipse, but because they're orbiting close to one another, they distort one another. And so as they pass through their periastron, their point of closest approach, the stars are maximally distorted, and light from one star reflects off the other star. And that causes a really interesting variation of their photometric brightness that looks a little bit like an EKG signature. And so that's why they're called heartbeat variables. And by modeling these EKG signatures, these heartbeats, it's possible to determine very precisely the masses, radii, and to test models of the internal structure of these stars. I told you that BRITE Constellation is not a system that is focused on detecting exoplanets. Nevertheless, this is a system that you're probably familiar with. This is Beta Pictoris. Beta Pictoris has a giant exoplanet that passes both in front of and behind the star during each of its orbits. And so BRITE Constellation was used, in fact, in tandem with the Hubble Space Telescope in order to try to detect a system of rings or moons, the so-called Hill sphere of Beta Pictoris b. And in order to do that, we observed the star itself with the BRITE satellites for over 200 days back in 2017 and 2018. At this point, we don't have any evidence of a ring system, unfortunately. So the last thing I'm going to tell you about is a serendipitous discovery. This is the discovery of a nova that has an ASUS name, so it's Assassin 18FV. So this is a nova that was first discovered by the ASUS supernova project. But then when we went back into our data and we examined the field in which this particular nova was detected, we discovered that we had been observing it before it had been detected by AAVSO. And so we have pre-discovery observations, as strange as that may sound, for this particular nova. Now, if you think about the constraints of bright constellation, the fact that the satellites can only observe stars that are very bright, and we only observe these tiny postage stamps, the likelihood of us detecting a transient object like this nova is very, very low, probably less than 1 in a million. And so what's being illustrated, this is an artist's depiction of the nova itself. This is the star that we were originally observing. This is the red giant in the postage stamp. And this is what it looked like after the nova had taken place. So you can now see that there are two objects of comparable brightness that are both present within the postage stamp. It's a very interesting light curve. We observe the rise up and then a whole bunch of flaring before it cools off and dies down. And so this is the object of an intensive study that's taking place with some colleagues at the University of Michigan. So just to wrap up, a tiny mission like Bright Constellation built on a small budget is naturally going to encounter some technical issues. The principal problem that we've had to deal with is radiation damage due to the CCD detectors. We've come up with some clever ways of dealing with that radiation damage, but what I want to show you is the evolution of the CCD detector of the Bright Toronto satellite over the last 3.5 years. So what we're seeing here are full frame images. This is prior to launch. This is 2015, 2016, and 2017. And you can see that the cosmetics of the CCD have become pretty disastrous. And this is all due to the impact of high energy protons in the Earth's severe radiation environment. So we're still able to observe. We're still able to get quality scientific data, but it's required some real wiggling on the part of our technical team in order to be able to work around these sorts of limitations. So I'm going to finish off with this slide. So this is a summary of the mission to date. So the entire constellation has been in space now for 6 years. Since observing started a little bit later, once we'd figured out the system, the longest data set that we have, in fact for the constellation of Orion, is about 5.5 years long. Because the satellites don't have any consumables, there's no fuel that's been used, so they're environmentally friendly. They've completed almost 150,000 orbits, traveled over 1 billion kilometers. We've completed 42 campaigns and observed over 600 stars. And at the moment, we've published 171 papers. And so I'm always excited to think about what it's possible to do with $1 million in your pocket. And so this is an example of Bright Constellation. Thank you very much.
Thank you, Craig. I think we have a time for one question, if anyone... Are you here? Jim?
You made a point about the little reaction wheel. Where was it made?
So the reaction wheels were developed by Sinclair Aerospace in collaboration with the SFL. So they're an at-home product, and in particular, they're home here in the north of Toronto.
Kieran Carroll's most reaction wheels.
I'm sorry?
Okay, so thank you very much.
Thank you.
Okay.